Hello and welcome everyone. I am Apoorv Badar, and as part of my elective on blockchain technology at BITS Pilani, I welcome you to this seminar on IOTA in 20 minutes. So, IOTA is a cryptocurrency developed and released in 2016 with an initial coin offering of USD 590,000 for 2.79 quadrillion IOTA, which compares with the 2.1 quadrillion Satoshis in Bitcoin. One of the key motives of IOTA was to develop a cryptocurrency for the Internet of Things industry and the micropayments required in it. But it has since expanded into many other applications, as we'll see. Compared to linked lists used in conventional blockchain technologies, IOTA uses Tangle, which is a directed acyclic graph for storing transactions. It offers features that are required to establish a machine to machine. First, I would like to discuss some issues and challenges faced by conventional blockchain technologies. The first issue is that of scalability. Due to the constraints on the average block creation time of around 10 minutes and block size of 1 MB, Bitcoin is limited to about 5 to 7 transactions per second. This is very low and thus leads to a long wait time. Although Ethereum is much faster, it is still less compared to the 2000 transactions per second handled by Visa, one of the leading payment processor of the conventional currencies. The second issue is that of transaction fees. With the growing popularity of cryptocurrencies, more and more transactions compete for the same block. This increased competition increases the transaction fees as you have to incentivize the miners to include your transaction. Currently, in 2022, Bitcoin has an average transaction fee of around $2.26. This makes it infeasible for microtransactions. We are not going to pay a transaction fee of around 50% to buy something for $5, right? Another issue is that of mining pools. In this, groups of miners combine their computing resources and form a single large mining entity, which increases their chances of success. This leads to centralization, which goes against the principles of blockchain. Also, there is vulnerability to quantum attacks. Compared to the linear time complexity required by a classical computer, a quantum computer would require only square root of n operations. This corresponds to a 17 billion times greater efficiency for 2 to the power 68 permutations when finding the nonce. Now, let's discuss IOTA and see how it promises to solve some of these challenges. IOTA uses DAGs. A directed acyclic graph is a network of nodes connected by directed edges with no cycles, that is, paths starting and ending at the same node. In IOTA, each transaction is represented by a single node site, unlike bundling up into blocks in Bitcoin. Each new transaction validates up to 2 to 8 previous transactions. An edge from a node A to node B means that the transaction B is approved by A. However, a single approval doesn't mean that the transaction is confirmed. As more and more nodes approve a transaction, its confirmation confidence increases. For example, if the algorithm is executed 100 times and the system determines that a transaction is approved by 70 out of the 100 times, we say that it has a confirmation confidence of 70%. Quick note on the terminology. Each node is called a site and has a height and a depth. The height corresponds to the distance from the genesis node, whereas the depth corresponds to the distance from the tips. Since IOTA has no minting of new tokens, all the tokens can be initially assumed to belong to a single node, that is, the genesis node, which is A in this case. Tips are the nodes with zero integrity, that is, the transactions which have no approvals at that point. These are the gray colored nodes as you can see. Each node has a weight which is proportional to the amount of work that the issuing node invested into it. For now, let's consider that all the nodes have a weight of 1. As an example to understand further, let's consider the node H. It directly approves the nodes D and E and indirectly approves A. So it has a score of 4, 1 each for H, D, E and A. Similarly, H is directly approved by K, L and alpha and indirectly approved by Q, S, P, N, O, R, U, V, T and W, X, Y, Z. Thus, the cumulative weight of H is 4 plus 3 plus 6 plus 3 plus 1, which is 17. Also, the deeper the node is, more is its confidence of confirmation. So, now let's look how a node issues a transaction. First, the node chooses at least two other transactions to approve using Markov chain Monte Carlo algorithm, which is a First, the node chooses at least two other transactions to approve using Markov chain Monte Carlo algorithm, which is a probabilistic model to select random. First, the node chooses at least two other transactions to approve using Markov chain Monte Carlo algorithm, which uses a random tip selection method to ensure that only honest transaction branches grow. In general, these two transactions selected might be conflicting. If conflicting directly or indirectly through some path, it will not approve one of them. Finally, it does the proof of work required by solving the cryptographic puzzle of finding a nonce similar to that in Bitcoin. First, the node chooses at least two other transactions to approve using Markov chain Monte Carlo algorithm, which uses a random tip selection method to ensure that only honest transaction branches grow. In general, these two transactions selected might be conflicting. If conflicting directly or indirectly through some path, it will not approve one of them. Finally, it does the proof of work required by solving the cryptographic puzzle of finding a nonce similar to that in Bitcoin. So, how does IOTA prevent double spending? After the arrival of a new transaction, a full node, that is, which is connected to all its neighbors, will walk backwards along the edges of the tag to the genesis, which is the first transaction, and check if there are any conflicting transactions. If there are, then this step isn't considered to be valid. So, to double spend, a transaction would have to outpace the entire input flow of new transactions. And since the tangle is network bound, the attacker would have to be everywhere. Thus, the input flow of honest transactions should be large compared to the attacker's computational power. However, this indicates the need for additional security measures, such as checkpoints with a centralized entity during the early days of a tangle-based system, since the number of transactions in the early day would be low when the number of transactions is low. So, the first version of IOTA did use a coordinator, a centralized entity, as we'll see. Finally, before we move on to the key features and applications, let's see how IOTA proposes to handle some attacks. The first one is that of large weight attack, since each transaction has a weight which is directly proportional to the amount of work that is since each transaction has a weight which is directly proportional to the amount of work that the issuing node invested into it. In order to double spend, the attacker can try to give a very large weight to the double spending transaction so that it would outweigh the legitimate subtangle. This strategy would be a menace to the network in the case where the allowed weight is unbounded. As a solution, the weight of a transaction has an upper bound. Also, the attacker may prepare a double spending transaction well in advance, build a secret subtangle referencing it, and then broadcast the subtangle after the merchant accepts the legitimate transaction. Thus, the cumulative weight is not a good metric to judge the conflicting transactions. A better method for deciding between two conflicting transactions is to run the tip selection algorithm and see which of the two transactions is indirectly or directly approved by the new incoming node, and see which of the two transactions is approved by the incoming node. A second possible attack is that of the parasite chain. In this attack, the attacker builds a subtangle containing the duplicate transaction to increase its height. This attack is also another reason which makes the approval strategies based on height or score obsolete, since the attacker's sites will have higher values for these metrics when compared to the legitimate tangle. However, once again, the Markov chain tip selection algorithm provides protection against this kind of attack too. Not going into the technical details of the algorithm, the basic idea is to place some particles, that is, random walkers, on the sides of tangle and let them walk towards the tip in a random way. The tips chosen by these walkers are then the candidates for approval, and this does probabilistically lead to selection of the honest transactions. Finally, let's sum up the key features. First, it has a zero transaction fee and involves no minting of new tokens. This is possible since the transactions approve each other and thus eliminate the need for fees. We can also think of the zero transaction fee as a reward for approving the other transactions. That is, it itself doesn't have to pay the fees. Second, IOTA scales really well. With the increase in the number of transactions, we have more and more transactions to validate each other, and thus it scales really well. Currently, IOTA can handle around 1000 fee-less data and value transactions per second, which is much larger than the 5 to 7 transactions per second handled by Bitcoin. Third, the first version of IOTA used to use a scheme known as the Winter's one-time signature scheme, which was quantum resilient. However, due to some issues leading to a big wallet hack in early 2020, it has switched to another method which is not currently resilient to quantum machines. Fourth, completely self-regulating. Instead of a small subset of the network being responsible for the overall consensus in the form of miners and stakers, the entire network of active participants, that is, the devices making transactions, are directly involved in the approval of transactions. As such, consensus in IOTA is no longer decoupled. As such, consensus in IOTA is no longer decoupled from the transaction making process like in Bitcoin. However, IOTA still faces some issues and challenges. Like I mentioned before, in the first version of IOTA, the input flow of honest transactions should be large compared to the attacker's computational power, and thus there was a need for additional security measures such as checkpoints. Hence, the first version of IOTA had a central coordinator which decided the transactions and data to be included into the ledger. Thus, the coordinator checkpoints valid transactions which are then validated by the entire network. It creates a transaction with a signature approximately every 60 to 90 seconds. Thus, the first version of IOTA was actually centralized. To solve this problem, the second version of IOTA, which was released in April 2021, uses manas. A mana is a scarce resource earned by holding and also transacting in IOTA based on some rules. You can also use manas to forward your transactions in the line. In this version, nodes vote on the conflicts through a voting protocol, fast probabilistic consensus (FPC), which determines which of the conflicting branches should be rejected. Thus, this voting is thus protected from attackers by mana, which acts as a reputation system which fairly limits who can vote. This voting is thus protected from attackers by mana, which acts as a reputation system which fairly limits who can vote, similar to the proof of stake method. After FPC rejects the bad branches, tips are selected from the correct branches for new messages to reference. As these correct branches gain more and more messages, we say that their approval weight grows. Once a branch gets enough approval weight, its transactions are finalized and booked into the ledger, and mana is updated, determining the next FPC voters. Thus, this resolves the need for the coordinator, making the network truly decentralized. Finally, let's look at some applications of IOTA. First, data integrity. Be it smart homes, automotive industry, and e-mobility, mission-critical infrastructure, or e-health and e-governance, all need a non-manipulable and secure exchange of data and payments for which the IOTA network can be used. As an example, the Volkswagen Group demonstrated a car-sharing model built via IOTA at CeBIT 2018. According to IOTA's vision, in the future, a car could have its own wallet and automatically pay for infrastructure and services like parking, refuel, and tolls. It has also partnered with Jaguar and Tech Mahindra for research in the field. Another possible application is in supply chain management. Supply chain requires syncing data securely, for example, status of delivery. If distributed ledger technology is used in this area, it is possible to determine, for example, that the cold chain, which is mandatory for certain foods, has not been interrupted, thus enabling claims for compensation to be met in advance. Finally, the key motive for which IOTA was built is the Internet of Things industry. The IoT industry requires sharing of bandwidth, computing power, and resources, which can be facilitated by IOTA on schemes such as pay per byte as you. It can also be used to standardize machine-readable contracts and create a system for secure communication and exchange of data, goods, services, and payments. Also, smart contracts, similar to those supported by Ethereum, are currently a work in progress. Thus, IOTA is certainly an interesting approach towards eliminating transaction fees and also scaling blockchain tech, and I look forward to see how it develops. This concludes the seminar. Thank you.